All right, bonding theory, explaining molecular geometry. Predict the shape of molecules and the bond angles within those molecules. Predict the polarity of molecules. Determine the hybridization of atoms and molecules. So we still do a little bit of hybridization. I mean, you're still expected to know that. We want to introduce it for something we decided on in our Gen Chem meetings where all the faculty that teach Gen Chem continue to do a little bit of hybridization. And this talks about another aspect of the shape of molecules. Chemical physical properties are related to molecular shape. Molecules have a three-dimensional structure which determines their activity. Biomolecules interact with molecules to fit into their active site. I think this figure talked about the chemical that's responsible for some of these flavors or something like that, and how it's related to the shape of that molecule. All right, so fluid structures, atoms and bonds and molecules connected in a way that we don't get a good sense for like the real shape of a molecule. If you have a little ball and stick hit, and you'll need to get something like this for organic chemistry, it helps to visualize molecules and you can see their shapes and things like that much better. So we'll use this today a little bit as we go forward. So it's tough to visualize something like a tetrahedral molecule like this and the bond angles when it's on a piece of paper, the methane over there. Okay, you see the 109.5 degrees, there's your ball and stick model. Three-dimensional, that's still a two-dimensional plane, but at least it's done in a way that makes it look three-dimensional and you can get a feel for it. So I made this analogy before. It's like holding balloons all by where they're tied and how they spread each other out. You think of that as the electron repulsion. As electron clouds there. And this is the steric number. It's the number of electrons surrounding the central atom, electron pairs. Okay. It doesn't matter if they're bonded or non-bonded. Okay. Steric number is simply the electron groups around the central atom. So obviously you can't have one. Okay. Because then you wouldn't have a central atom. You just have two atoms. So the central atom is effectively this, and there's two groups around it, steric number of 2. Okay, so you can't have a 1. You got to start with 2. And then you got 3. And see how they space each other out? 4. There's the tetrahedral. That's the methane, right? 109.5 degrees. That's the way they're going to structure themselves, 360 degrees around a central atom. And then you got 5 and 6. Okay. And this is Vesper's theory that's going to do this for us, help us get to these shapes of molecules. This valence shell electron pair repulsion theory, or Vesper. We must determine the number of electron pairs, both bonding and lone pairs, around the central atom, which determines the electron pair geometry. Some people call it, I learned it as electron domain geometry. Electron pair, electron domain, just semantics, same thing. So draw the Lewis structure, okay? Can't go anywhere without chapter 4. From the Lewis structure, determine the steric number. And that is basically just count the pairs around the central atom. That's it. Bonded or non-bonded, we don't care, just count them. Number of atoms bonded, number of lone pairs on the central atom. Determine the optimal arrangement of pairs to minimize the repulsion, and these are your choices. Okay? Linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. Now, the molecular geometry actually describes the 3D arrangement of the atoms, which are going to be the bonded ones only. We don't care about the lone pairs because remember, electrons are just kind of waves. Until you bond something to them, that kind of localizes it. Okay? It's the same way, it's like kind of like when you detect something, that collapses the wave function, and then you can measure it. Otherwise, it's a wave in space until you go to measure it. So the idea that then electron is a point doesn't make any sense anymore. It fills the entire orbital, okay, all the time, just like light. Where's that light? Well, it fills the entire room all the time. It's the same thing with electron. When you measured it, that collapses that wave function and effectively forces it to localize, and then you can treat it as a particle and measure it. Kind of like when bonding happens, that forces that electron wave to collapse into a region, and now you have this, if you will, I want to say solid structure, if you will. That's part of the molecule now, when you have an attached atom that can, be measured and that can bond to something, things like this. So that's all we care about is the atoms. I mean, I should say that's all we care about, but that's what molecular geometry is meant to determine. What is the structure of the atoms? How are they arranged around the central atom? Okay, so if the central atom has no lone pairs, then the molecular geometry is the same as the electron geometry. So if they're all the same, linear is linear. Octahedral, that's the electron domain geometry. It's also the shape that they're all attached. So it's the molecular geometry also. That's all this means. If these are all attached, then this is octahedral on the right. I do my pen. And that's going to be the electron domain geometry and the molecular geometry. Okay? Does that make sense? But if some of them are lone pairs and some of them are atoms, now you've got something different going on, right? And you're going to have different names. And that's what we're going to do, come up with all different names for these based on kind of what they look like. So these are examples of molecular geometries. And this is cases where all the atoms are, all the electron domains are attached atoms. So you got SF6, so that's octahedral. Now you can see it. It's got 4 atoms around the equator, right? Equatorial, we call those. And then 2 axial, top and bottom, right? That's SF6. Okay. Then you look at TF5, that's trigonal pyramidal. It's got 3 around the equator, and then 1 at the top and bottom, the 2 axial ones. Tetrahedral, then they're all just spaced equally around that central atom, 109.5 degrees. Trigonal planar, what's the angle going to be there? That's flat, so what's the angle going to be? What are the degrees in a circle? How many? 360 divided by 3 is 120. Those will be 120 degree angles here. Right? Because it's planar, it's flat. Okay? And then, of course, linear, like CO2. These kits are not good for certain things. I don't think they have a, so I'd have to, no, can't do that one either. Do a trigonal planar in these kits, at least this kit. Can't even use a tetrahedral, it's the wrong angle. All right. Let's practice then. We've already seen methane already. So the Lewis structure then, of course, of methane is and that, of course, is tetrahedral. The CH2O or H2CO, however you want to write it. Carbon's definitely the central atom. Sometimes the central atom is written in the center to give you an idea, but sometimes they're written first. So I said there's no super steadfast convention. So how many valence electrons for this one? 12. Central atom. What do I need to do? Right, double bonds. Let's erase one of those. And then we'll be good. Actually, we've done this one before. So what's the shape? What? Trigonal. Trigonal planar. Even though it's not drawn as trigonal planar, this is a correct Lewis structure, right? Right? I've written it as T-shaped. I mean, that's the way I've kind of drawn it. But that is an actual shape we'll see later. But you can't go by the Lewis structure. You just have to say, okay, you have to say your steric number is 3. That's it. And there's no lone pairs. So steric number 3, trigonal planar. You can't look at the Lewis structure and deduce the shape because the Lewis structure can be drawn incorrectly shape-wise. You got to look at your steric number. Questions? Okay, so now, whoops. Molecular geometry, center atoms with lone pairs. Starting with steric number 3. This is the ozone molecule. So we saw this already. So there's, 6 times 3 is 18. Okay. So you've got 8 and 8 is 16, and then 2 for the lone pair is 18. So there's your Lewis structure. This has resonance, so the double bond could be on either side. If you're just drawing one and not doing the arrow, either one's correct. The electron domain geometry, that's just steric number of 3, so that's trigonal planar. But the molecular geometry is bent. You see, we don't consider that lone pair. We're just interested in the atoms. And that's bent. Some people call it angular. Questions? We good? Now the bond angles around central atoms with lone pairs are less than those predicted due to electron repulsion. And that is normally this would be 120 degrees, right? Trigonal planar, but it's only 117. Why? That unbonded pair takes up more space, pushes the other ones down like this. I guess that's kind of messing with me. So it's 117 instead of 120. Okay.
Both of those, the
trigonal planar,
or whatever, and then the other one, they're both correct. It's just like different ways of looking at it.
Oh, you mean this here?
Yes.
Yeah, it depends. That's right. I mean, when you're talking about molecular geometry, this is the only thing that's correct. Bent. If you say trigonal planar, no, it's not. So yes, one is the steric number of just pairs of electrons surrounding the central atom, whether bonded or unbonded. This is the one that tends to be more important for things like, drug design and toxicology, understanding binding to receptors of enzymes and substrates and all that kind of stuff. It's the molecular geometry that's going to be key. Does that help?
Yes.
So the biggest repulsion would be 2 lone pairs repelling each other. The next would be a lone pair and a bonded pair, and the least repulsion would be 2 bonded pairs next to each other. Okay, and you'll see that with angles. You'll see the angle get, if you go smaller and smaller as you get more lone pairs. Okay, let's do steric number 4. So all of these 3 right here. I guess there's only 2. I thought methane was on here too. It's just ammonia, water. We could say ammonia, water, and methane. All of them are tetrahedral electron pair geometry. But their actual molecular shapes are different. Methane has no lone pairs, so its shape is the same as the electron pair geometry, tetrahedral, with 109.5 degree angles. Ammonia has a lone pair, so its angle should be slightly less than it is by 2.5 degrees, 107. So here you go. This model does not change the angles, but at least it gives you an idea. This is tetrahedral, right? Right? Pull off a pair. That's ammonia. You got a pyramid now. It's like a trigonal pyramid, right? Pull off another pair. I have water. Now the angle's not changing. That's going to be 109.5 there, but we know it's going to be less than that. But still, you get the idea. You take tetrahedral and just pull off pairs. And now these are lone pairs here, but in terms of molecular geometry, that's it. It's just bent. And that's what you're seeing here. So with water, it's 100 down to 104.5. Those 2 lone pairs, and they're both up top. This is the key that makes water bent. Why? Because they can get more space that way and push the other atoms down if they're both up there. If one's here, one's here, and they're trying to do this, right? They're pushing them in opposite directions. So put them both in the same area, push these atoms down. It gives you a little bit more space. So this is all steric number 4, but now you've got 2 additional shapes, depending on whether you have bonded or non-bonded pairs. Don't get trigonal pyramidal confused with I didn't realize trigonal was a word that was going to trip people up. It's pronounced trigonal pyramidal. Don't get that confused with this one here, which is trigonal bipyramidal, which we'll come up and do in a bit. Steric number 5. There it is. Trigonal bipyramidal. Okay. 5 groups. This one here. Five groups surrounding it. Now, I'll turn that on in a second. So, if I take, so let's look at this molecule again. You might ask, well, which one do you take off? It doesn't matter. It's completely symmetrical, right? Take any one you want off. Okay, it doesn't matter. The shape winds up being the same. Wait, that's not right. This is it. Yeah. So I've got. No, it's not. Not for this one. I'm confused. That's not neutral. So this is 90 here. These are 120. So where's that on the figure? Go back and look. I didn't see it there. With one lone pair. Okay, there it is. But why does it say central atoms can have either 2, 3, or 4 lone pairs depending on the sites in the triple bond middle. You have one lone pair. It's right there. Why did they say 2, 3, or 4? Here, let me see the book for a second. So if you take one lone pair off, the key is you take, I'm just getting confused off the people, sorry. You take it off from the equatorial position. Why? Because giving it more space, I guess I can do it here. So we're going to give it more space this way. Okay, so if I take it off, okay, here it is here, the 2 axial, I'm holding it by the axial, and there's the equatorial, right? Okay, if I take it off from the equatorial, my lone pair now is 90 degrees from only 2, the two axial ones. It's going to be 120 from these others, right? If I was to take off an axial one, then it's 90 degrees, the lone pair, away from 3 of these. So that's going to create more tension. You see? 90 degrees obviously is less than 120. So by pulling off an equatorial one, I'm only 90 degrees from 2 of the attached atoms. And I'm 120 from the others. So that's why when you have a lone pair, you get it from the equatorial position. I just want to see what the book seems to be confusing here. Why they say 1? Why they say 2, 3? Got a bunch of mistakes in there. They're slides. Oh, that's the mistake. Wait, no. Yeah, so theoretical. Yeah. So this should say this should say 1, 2, and 3. Okay. 1, 2, and 3. Okay, so there is seesaw. Okay, and you can kind of see, I'll show you in a second, 2 lone pairs, T-shaped, and 3 lone pairs get you linear. So let's do this. One lone pair, there's your seesaw. See, chemistry can be fun. It's kind of like Legos. I was a big Lego fan, and I got my son into it. So it's kind of fun to play with models. 2 lone pairs. Let's take the next one off, and there's my T-shape. It's planar now, right? They're all in the same plane. 3 off the equatorial. This is the equatorial still I'm pulling. I've got the 2 axial left, and then I got linear. And that's why they don't bother with 4, because then all you've got is 2 atoms left, and obviously has to be linear when you take 4 lone pairs off of 5, off of 5 attachments. Okay, so those are your shapes. And then you've got the last one, the octahedral, which is 6. And let me get the octahedral out. This is the one that doesn't matter where you take that first electron from, because it's completely symmetrical. Okay, so And the next one you take off is important though. So let's look at this. So the first one you take off is octahedral, and you get this square pyramid, right? You see it? Take a look here. Here it is here. It doesn't matter where I take it off because this is completely symmetrical. You say, well, it's not. It's got 4 there, but you can turn it any way you want. It's got four equatorial and 2 axial. I'm actually spatially challenged. So some people are really good at, I'm too analytical this way. You know, my wife's got the more art gene, and those people are more visual, spatial. How many of these people needs a GPS to go get a gallon of milk? I'll get disoriented and lost. So I don't visualize things well. So models are great for me. But if you take this off anywhere, it's the same. Doesn't matter. I get this square pyramid. And you can see it. The bottom is square. The idea is this right here. Top, bottom, 2 sides. That's your square. Some people are like, what's a square? It's an X, you know? Well, draw the lines. You got to draw the lines. Make it square. And it doesn't matter. I'll take off this one instead. Still a square pyramid. The next one you want to take off is to get these lone pairs opposite each other, 180 degrees apart, is the other axial one up here now. And now you leave that like that, and you get the square planar. That's the next one, right? And then there's others after that, but they're kind of rare. You can obviously pull off one more and get T-shaped. That's not in your book. They only have the 2. But T-shaped is more common with the trigonal bipyramidal than it is with octahedral, but it does happen. It's just not that common. And then, of course, you pull off another one, get linear and all that. They're just not that common. And this is the key table. You know, in past semesters, I say to my students, you know, learn the names, learn the table, make a cheat sheet. Next time you're at a party, drinking a beer, you whip it out and you just start memorizing, memorizing your names. But you guys don't have to worry about that because you have an open book, open note. So you'll be able to just look at this. And the key is just to recognize the number of bonded pairs, right? And non-bonded pairs, and then the name that goes with that. And the book, and you have some examples here. So look at this one, IF5. They're all halogens, right? You think halogens only take on 1 bond. How do you have IF5? Well, iodine's down low in the periodic table. It's got all these d orbitals available to it, and fluorine's the more electronegative one, so iodine's a central atom, and it binds with fluorine. It forms a compound. Questions? I'm going to stop there.